Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you're watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right, hello everybody. Welcome to another episode. Ask us anything about.
I'm like a weatherman.
Yeah, that's
See,
right.
it's like, I can't do it. Crap. Oh, there we go. Yeah, no, I can't put my hand. 100 episodes.
100 episodes.
See,
right here.
you gotta like point. That's hard. They do that. You know, weather people. They point to, like, this is a high pressure system. It's moving over the city, and you're like, how do you know where your hand?
How do you know where your hand is?
You have to. I guess they have a monitor, and I can see
Yes.
where my hand is compared to 100 episodes. I want to hold it up.
Yeah.
We didn't get the noisemakers. The
Yeah, I
that
know.
make the sound.
I asked our admin to see if she could find noisemakers. Couldn't find
Oh,
them.
we didn't have any. I didn't know you
That's
asked.
okay.
I just totally forgot until this very moment. So I'm glad that you did any sort of effort at all, because my effort was to say that we should do it and then do absolutely nothing. But welcome everybody, and we're happy you're here because this is our 100th episode. We're very excited. Yes. 100 episodes of answering the questions about electrochemistry. So it sounds less exciting when I say it that way, but it's 100 episodes.
Yeah.
And I think that's pretty cool.
Yeah.
And I'm very excited for us.
Yeah, that's right. I would have like fun, like sparkly beverages or something, but can't. Probably shouldn't do that. Even if it is like apple cider, it's like I probably can't drink anything.
I don't know that our boss would be happy to watch this episode later.
That's right.
And be like, were you drinking in the office?
Yeah, that's right.
Absolutely not. It's definitely not pure vodka. That's not what's happening. Plus, the answers to the questions by the second hour would be like, look, research is hard. Okay. And then just like falling asleep.
It's the coefficient.
Yeah, the diffusion coefficient is that's acting. I'm not drunk. I swear. I have had no alcohol. I don't even really drink anyway, so this is not a good example. Okay. That was a fun start. Welcome everybody. Thank you for being here, and truthfully, very earnestly, thank you for 100 episodes. We're thrilled to do this. And let's get right to it. So Ahmed had a few questions, and keeping with the celebratory theme, your first comment, thank you very much. You said, first, I want to seize the moment to thank you for answering my questions every week. I am collecting my thoughts and questions to get a valuable answer for you. Well, I hope it's valuable. We're doing our best, but I appreciate the comment, Ahmed. So the first question is, do you think it's better to wash copper foil by organic solvents such as acetone or ethanol to remove any impurities before performing coulombic efficiency measurement for a lithium copper coin cell? So yes, I do. You should always rinse, what we would call it. You see it in the literature, like as received, something like that, right? As received copper or lithium or whatever. Maybe don't rinse lithium because obviously put lithium in contact with aqueous, although you said non-aqueous. But my point being, with the copper, for example, it is a good idea to rinse it. I think I used to. I'm trying to remember what I used to use. I probably used, for example, when I was in graduate school and I was testing with anode materials, copper is used as the current collector for anodes in a lithium ion battery. Okay, so I would use copper foil as well. And I think probably the method that I would use is something like acetone, which is really good. Acetone obviously will remove a lot of organic impurities, as well as it's water soluble, and it's what's the term? A polar aprodic, I guess. Polar prodic, whatever it is. Acetone's a great solvent in any case, and it's good to clean. And then I would rinse it maybe with the solvent that I'm using in my battery. So in my case, it was something like dimethyl carbonate or diethyl carbonate or ethylene carbonate. And so sometimes it's a good idea to do that as the last step, is to rinse your foil or your electrode with the electrolyte that it's about to go into. So any residual liquid on the material is identical to the electrolyte it's about to encounter, if that makes sense. The only thing I want to add is that it is pivotal to dry or wipe, really remove the solvent, especially if it's something like ethanol or acetone. Now, acetone's pretty volatile and evaporates pretty easily, so it's unlikely that you're going to have like residual acetone hanging around if you're at room temperature, for example. But just to be clear, like if you were to rinse it with water or something, I know you said organic, but you don't want to have any residual solvent. Now it's like you got rid of impurities, but now you have solvent making its way into your cell. And so just avoid that. So be careful that you, after you've rinsed it, to remove any impurities, that you remove the solvent as well. So just make sure you do that step. The next question is, are there any methods to ensure about purity of a separator surface? It's hard to be washed before using, and they are highly susceptible for contamination during the cutting process, and this can influence, I guess, the counter electrode. So yes, it can be, and it's a lot of times as rudimentary as using like a pair of scissors to cut a piece, like a square piece of your separator, or maybe a circle. Sometimes they have like punch presses that cut out a circle if it's like a coin cell. The first thing I'll say is that that is a legitimate concern. Let's just say having contamination around the edges where it was cut, the blade or whatever device, scissors or a punch. It's cutting multiple things multiple times. It could have contamination around the edges. One of the ways that naturally helps isolate that to some degree is the fact that the separator should be wider and larger than both the anode and the cathode to ensure separation. So to a certain degree, impurities around the edge of this piece of separator where you cut it are a little bit less likely to interact with the cell itself, because I'm like drawing in space. Let me just I think this is clear for the most part, but just to kind of show what I mean. Like your separator is this big, right? And your anode and your cathode are this, this big, right? Okay, whatever. Maybe they don't perfectly match up and line up or whatever. But the point is, if there's like impurities out here and this is all dirty around here, it's like, okay, well, this is the area of interest, right? All in the middle here. And so impurities around the outside are not ideal, but one of the ways you get around that is that the separator is wider than the anode, than the other electrodes. As far as rinsing it though, I mean, it can be possible to rinse a separator as well. Like it's going to be exposed to the same electrolyte. So in theory, what you could do, again, it's like if I'm using dimethyl carbonate, propylene carbonate, whatever, you could rinse the separator in that solvent a little before you use it. That could be a possibility as well. But it is, I agree. It's a piece of plastic. It's a little harder to like grip, and you don't want to rip it. There's logistically and mechanically, it can be tougher for sure to rinse, but it can be done. I think in that regard, you just have to also be careful. Yeah. Cause like some other solvents, like maybe acetone or DMF or something could dissolve the membrane itself. You're trying to rinse it, it ends up destroying it. So be careful about that. But you might be able to get away with using the electrolyte itself as a soak or a rinse step to try to remove any impurities. And then the last question, and then I see there's a few questions live we'll get to for sure. From Ahmed is, which is better for dissolving the electrolyte, using stirring, vortex mixture, or shaking by hand? Can the method of dissolving the electrolyte influence the coulombic efficiency of a lithium copper coin cell? So what you want to do is you want to take your solution and just shake it like crazy. It's going to spill all over the lab. It's going to get in everybody. No, I'm just kidding. It doesn't matter. It really doesn't matter. Can the method of dissolving the electrolyte influence the coulombic efficiency? Yeah, of course, if you don't dissolve it properly. So something like LiPF6 in, lithium carbonate or whatever in propylene carbonate or dimethyl carbonate, usually you do up to like 0.5 or 1 molar. You do like a high concentration. And it's harder to dissolve in non-aqueous than in water in a lot of cases. It takes a little longer and it can be a little trickier. So you just got to be patient. There's no, like, the method of dissolution is irrelevant. you know, I would guess manual stirring, like, I don't know, like a metal spatula or a plastic, whatever you're using, right? Something hopefully that don't introduce contamination, of course, is probably a very nice way of doing it, but it's a lot of manual labor. So people will likely put it onto a stir plate and have put a stir bar and just let it spin for a while until it's dissolved. That's fine. Um, you can swish the solution around. Sometimes you have to like press with a, implement like a spatula and break, so you get chunks of the salt that are like stubborn and won't break up or something. So you have to break them up manually. Like, these are all normal kinds of things. The only way it's going to influence your efficiency or your results more generally is if it's not all properly dissolved, which, it certainly can happen if you're just not patient enough. So, what I used to do, for instance, is I would make a batch of like 1 molar LiPF6 in like a mixture of carbonate electrolytes, and leave it in the glove box, like store. Like, I would make like, when you make a coin cell, you usually use, I don't know, a milliliter at most, 500 microliters. Like, you're putting drops of it into your coin cell. If you're doing a larger system, you might use a few milliliters. But I would make like 100 or 500 milliliters of it at once, and then like I said, it can take a little while for the LiPF6 to dissolve, just because it's stubborn, and it's not saturated, but it's close. It gets pretty close. So it can be a little bit of a time consuming process. So I would let it stir for a day or hours. I don't know. I can't remember honestly how long it took, but I would have it prepared ahead of time so that it was, there's no crystals left and it was fully dissolved, so that when I went to make my battery, I was at least sure that the electrolyte that I'm claiming I'm using is what it is. And it's not, it's actually 0.6 molar because it's not fully dissolved yet. It's just a timing thing. So don't worry so much about the method. Just make sure that it's dissolved when you're using it. That's all.
All right. Well, Ahmed did a good job if he wanted to get all of his questions answered ahead of time, because he does know it does get a little busy with all the questions that we end up
showing
getting.
up like 30 minutes in advance. That's the smart thing to do.
Smart thing to do. Next question is from Ramsa. Ramsa asks, what is the difference between polarization resistance and charge transfer resistance? So when I think about this question, to a certain degree, I think they are similar, and yet they're kind of used in different circumstances, different chemical systems. So polarization resistance is typically done for like corrosion studies, when you have, say, you have a coupon, some kind of thing that's corroding. You apply a linear sweep, a very slow linear sweep to that thing, to that electrode, and you get a current. And literally the angle of the current versus voltage is the resistance. That's the polarization resistance. The charge transfer resistance is something that's commonly determined via impedance spectroscopy, and the charge transfer resistance represents, in a way, the resistance for electron transfer. It can also be expressed as a rate constant for a molecule to undergo an electron transfer reaction. So in a way, I think they're actually very similar things. I think it just depends a little bit about what exactly is the application, which term is used more than the other. I don't know if you know about any other differences between those two concepts: polarization resistance and charge transfer resistance.
It's not. It's funny because it's like they're both resistances technically, right?
Correct. Yeah.
It's just I'm struggling almost because, like, if you were to have, no, it wouldn't be the same. So I think what's weird is that the way they're obtained is wildly different most of the time, right? The polarization resistance is typically obtained through a slow scan voltammogram.
Mm-hmm.
The charge transfer resistance is primarily obtained through impedance spectroscopy, because the charge transfer resistance. Now, okay, let me back up just briefly, right? Both of them are resistances. Resistance is fundamentally the ease or difficulty with which an electron moves. Correct. Or is transferred, right? It's a resist. That's sort of the definition of a resistor. It's an electron moves from point A to point B across this. For this purpose, it either happens really easily or really difficult
Yeah, that's very difficult.
With difficulty. That resistance is the measure of that. Now, the charge transfer resistance is specifically with respect to a Faradaic process. Polarization resistance is kind of like that, but it's more with relation to a corrosion process. But it doesn't necessarily have to be. It could, polarization resistance is done over a very narrow range.
Yeah.
And
impedance, if you think about it, it's like you're applying the sine wave across a narrow range.
It's just the charge transfer resistance is a very specific frequency, like range, related to a Faradaic process of interest. And so it isn't clear to me, for instance, if you were to do a polarization resistance where you just basically sweep the potential slowly over a short range, you get a slope, and that slope, as you said, is either the resistance or the inverse of the resistance, depending on where E and I are on your plot. That is a charge transfer resistance necessarily, because you're at it's not the same frequency. Like EIS allows you to have a frequency dependence. You know what I mean?
Yeah, but the resistance wouldn't change as a function of frequency.
If it's just a resistor, that's right.
Yeah,
but like in a real system, the charge transfer resistance is, like the width of a semicircle, right? And on a Bodhi plot, and that occurs over a range of frequencies because it's coupled with a capacitance, which is frequency dependent. And
but that resistance value is based on the potential that you're doing. So if you have different potentials,
what potential should I do impedance
at? You should do it at OCP, because that's where everything's happening.
Yeah, that's exactly right.
I think what we're ultimately getting at is that
almost like maybe they're more equivalent than I don't compare these two concepts. Honestly, very often.
And that's why he's asking the question.
Yeah, no, it's a good topic. It's the more we talk about it, the more you're making me think. Yeah, I mean they're similar phenomenologically.
I would say one thing that's interesting. It's because polarization resistance is used a lot in corrosion, and a corrosion process doesn't always undergo the same kind of like mass transport things, like when you're oxidizing, steel or iron or something. In polarization resistance, the nature of that reaction is very different than like the charge transfer resistance of like a homogeneous electron transfer of like ferrocene or ferrocyanide, like moving towards the molecule. The nature of the electron transfer is different. But at the same time, it is, as you said, like a Faradaic process. They are both Faradaic processes.
Yeah.
So maybe they are strangely very similar, but not exactly the same, just because of the context of when you use one or the other.
Yeah, I think that's kind of how it is.
Hopefully, Ramsa, that was helpful. We'll get to your next question now, which is, what is the difference between the symmetry factor and the transfer coefficient, and are they potential dependent? So the symmetry factor and transfer coefficient, this comes from electron transfer kinetics, Butler-Volmer theory, and I think that they are considered. I believe they are the same thing. That the symmetry factor and the transfer coefficient both relate to the same thing, because ultimately, and actually, I think I have some slides on this. Give me 1 second, because I've been thinking about this. All right, so here, okay, all right, here we go. So in the Butler-Volmer, can everyone see this? This is
yes.
Yeah. Okay. So this is so you have like regular electron transfer. This is from Butler-Volmer kinetics. And then when you look at this transition state and you change the potential, you get a change in the transition state. And this is where the whole like symmetry factor and transfer coefficient come in. It's the idea that the potential that you change to drive a reaction forward does not, that amount of energy, change in free energy, is not equal to the change in the transition state. And because the angle of these two lines, this blue and red line, can vary, we represent that as this like transfer coefficient, as like a fraction of the reaction going one way or another way. So the transfer coefficient is a way to represent like the symmetry, if you will, of this system. So I believe that those two things are actually the same. They are the same word or phrase, but the transfer coefficient does refer to alpha. Sometimes it's also called beta in some texts. And in Butler-Volmer kinetics, the alpha transfer coefficient is basically potential independent. But according to Marcus theory and other theories of electron transfer, the transfer coefficient is potential dependent. So that's kind of there are certain situations where like, oh, you get a Tafel plot and it's nice and linear, but when you reach a certain potential range, it starts to deviate. And so because of that, some people suggest, and even in some of the mathematics, you do get changes in like the transfer coefficient as a function of potential. So that is the so that's hopefully the answer to your question, Ramsa. If you have any further questions or need additional clarification, just let us know.
Let's see.
Silicon.
Yeah, silicon is next.
Silicon is asking how we select the salt bridge electrolyte. Well, usually the salt bridge, you use that when you have, say, your electrochemical test solution and then a reference electrode in a separate container, and use a salt bridge to connect the two. And it depends in many ways what is your limiting or contaminant system that you're trying to, the reason why you're preventing these two electrodes from being next to each other. Usually you're worried about the reference electrode contaminating your electrochemical test solution. So you usually have the electrolyte of the salt bridge be the same electrolyte of the electrochemical test solution. It wouldn't be the same electrolyte as like the reference electrode. That's typically the kind of electrolyte that you use. It would be the same as whatever your electrochemical test system might be. So I don't know. I don't have any other further things about it. But silicon, if you want more descriptions, like how do you select it? It should be the same as the test solution for your electrochemical system.
I would say that I think it's possible. I don't have like specific examples, but like publications like on at my fingertips, I suppose. But like, let's say you're testing in acid and you only have a silver chloride reference electrode and you want to avoid chloride in your main solution. This is one of the reasons to use a salt bridge, so that the silver chloride with like 4 molar KCl is over here, right? And your cell is over here. And so the chloride won't make its way into the main solution if you use a salt bridge. So to your point, what do you use? Well, like you said, it's a lot of times it's the main solution.
Mm-hmm.
So like you have this situation where I just wanted to note one thing that is a possibility, because I think it's probably what you said, but there's probably two, possibilities. So if you have your main solution here, right, and this is like H2SO4, okay, whatever, and you don't want chloride, no chloride, right? But you have your HeCl reference with 4 molar KCl over here. That's supposed to be a K, and I can't draw. Okay, KCl over here, right? So what you do is you use a salt bridge, and so you're separating it. Okay, so this is KCl over here. This is H2SO4 over here. And so one option is to put H2SO4 in the salt bridge, as you said, right? So the chloride contamination is taking place right here, if there's any slow leakage of chloride. And the time it would take for the chloride to move its way all the way here would be like an eternity. And so it's very unlikely chloride's going to like diffuse, like very minute amounts of ions are going to make their way. You can do the mathematics out. It's like, we've done it. It's like years. It takes forever. It's not, unless there's like forced convection of some sort. It's like it would never basically make it there. Another option, though, which can be in the case that like you have, you don't want the H2SO4, for instance, to make its way in this direction for whatever. Like, let's say that the main solution, it's both, right? You don't want chloride in your main solution, and you don't want the main solution in your reference electrode. Well, another possibility is to use a third solution of some type that's more neutral to both, right? Just as an example. So this right here is 4 molar KCl, and this is, 1 molar H2SO4 or whatever. Okay. Well, one possibility, for example, is, okay, in my salt bridge, then I could use something like KNO3. Right? That's relatively neutral. The K is, you have potassium common between the two. That's kind of nice. And nitrate is really like benign. It's unabsorbing. It doesn't do anything. You could do NaClO4. Potassium perchlorate is really good. Perchlorate is notoriously non-adsorbing. So on an electrode surface, perchlorate will never, typically it's assumed, adsorb and block active sites the way chloride does, which is why you don't want it with platinum electrodes, for instance. So that's just a possibility. I'm saying, like, that's another option. So if you have concerns about either direction, you could use some sort of neutral, so to speak, electrolyte in the salt bridge. And then, just be aware that you could have ClO4 in your acid, or NO3. Maybe that doesn't matter. Probably doesn't matter. You could use potassium sulfate, for instance. So there's a common sulfate there. In fact, maybe that one's, K2 SO4 is a good option, just for example, because then you have sulfate over here, like there's common anions or cations on either side. It just prevents, possibility of contamination in all directions. So that's just another option I wanted to mention as an alternative way to treat your salt bridge solution if you don't want to use the same electrolyte. But of course, mainly it's just to separate the reference electrode from your main solution.
And while we're on the subject, I see Anonymous has some questions, but I think we can answer RK Dodamani. What?
Dodamani.
Dodamani.
Yeah.
Dodamani's question, which is, why can't we use a copper wire instead of a salt bridge?
Well, you can.
Yeah, I guess you could.
But it's a bad idea.
Yeah. He may be referring to like the orientation of a salt bridge of, like, you have two cells, and then instead of them being connected with a salt bridge, they're actually connected with like a copper wire.
Oh, is that what you're I was thinking, is he using a copper wire as a pseudo-electro reference?
Oh, yes.
I don't know which one you mean.
I was thinking of,
like instead of like a paper towel or a tube or something
like that,
you just use a copper wire.
He's saying use a copper wire.
Oh, that's fun.
Like, he's saying, like, oh, a lot of people have like these two cells.
Yeah.
And then there's, like, I don't know, a voltmeter or something. So there's one electrode here, and then there's another electrode here, and there's some solution. But he's talking about, like, okay, normally you have a salt bridge, which is this guy, and maybe I'll make it blue just to be a different color.
Yeah.
Right? Like, why can't this salt bridge be why can't this be copper? That's a really interesting question.
Yeah. If that's what is meant, that seems likely. My brain went to like pseudo reference.
Oh yeah.
So my answer of you can is incorrect. You can't.
For this.
Yeah.
For this.
Anonymous, we didn't skip your questions. We were just we're just continuing the salt bridge discussion.
Yeah, we're continuing the salt bridge discussion.
I got you. I have a whole set of slides on fuel cells. I'll get to you in a second, I promise.
Yeah, so why would we not be able to use copper in this case? I think in principle,
because it won't transfer ions. That's an electrical conductor, not an ionic conductor.
Why can't you just do another? Why wouldn't it just do another electrochemistry experiment?
I don't know if it would.
Like, you have a electrochemistry happening here,
yeah,
and this just basically acts as like a counter electrode.
Would you have
on both sides?
Would it naturally generate its own electric field between the two sides to transfer basically electrons from left to right or right to left to balance its own circuit? Would that happen?
I think so. Because there's a whole field of bipolar electrochemistry, just based on this very same topic.
That's interesting. I guess I don't know. My assumption is it would not work because the purpose of the salt bridge, of course, is to balance the system. In this kind of a cell, which is like a galvanic cell, right?
Yeah,
is that what it's called?
Yeah, like in this case,
we have like copper and zinc on one side.
Yeah,
right?
yeah,
You know,
maybe you have
and you
copper
have
and
the thing.
zinc
So
or
the point
something.
is the electrons go from left to right or right to left, right
Yeah.
across the voltmeter.
Yes.
And then the reason why you have a salt bridge, which is usually either a tube that connects the liquid electrolyte, or it's like a paper towel or something as silly as, paper, but it's something that that physically connects both sides. That allows, so if electrons are moving from left to right, it means that negatively charged ions move from right to left, and there's a balance of charge. But that's the point, is that you can't have electrons going from left to right or right to left endlessly. There's no balance. It won't build up charge on one side like that. You have to have a balancing, or there's no electrochemistry that's going to happen. So the point that you're saying, I don't doubt what you're saying. I just actually I do doubt what you're saying. I'm not. It would be cool to see if that would work, because I fundamentally, if you have electrons moving from right to left, then electrons could move from left to right through the copper.
Yeah.
But that has to happen for a drive. There has to be a driving force to make that happen, which means that there has to be an electrical field across the copper itself.
Yes.
From left to right, or whatever the right directional analogy is here, which means that in the solution on the left and on the right, there has to be some difference in their potentials to be driving. I suppose it's possible.
It's a galvanic cell, so there's a difference in the potentials that's going to drive something.
I guess in theory it could work.
So you could do it, but
how come no one's done that? Has anyone ever done that?
So there's a whole field of like bipolar electrochemistry.
Yeah.
This is what the only person I know who does this, it's called bipolar electrochemistry.
It sounds like the electrochemistry is really happy sometimes and really
sometimes,
sad
yeah. But the idea is like you have and Richard Crooks is someone I know who does this.
Oh, okay.
But it's kind of wild. It's like he has a working electrode here, so this is like working, and it's like connected to a potentiostat, and it has a counter over here, and it's all in like an electrochemical cell. So all these things are in solution, and then he'll just have like a rod that's not connected to anything, and you'll start to develop some positive charge here. Let's say you're applying a negative charge here, or your working electrode's like negatively charged, and then your counter electrode's positively charged, and you'll develop negative and positive charge.
Yeah, to counteract it or whatever.
Yeah,
so
it's in a field.
What metal is that? Just any metal?
Any conductor. And if it feels,
I guess it makes sense. Field, like there's a field in the solution when you have electrochemistry happening naturally. So I guess it makes sense that the field will settle into a conductor if it's there.
Yeah,
that makes sense.
It'll feel it.
Yeah.
Now to answer to talk about RK's question a little bit more, like why wouldn't somebody want to do something like this?
Yeah.
Well, because if you have to have a reduction reaction occurring on your copper for the electron to transfer, because unlike the salt bridge is just moving ions relatively freely, but for the electron to move charge, it's got to undergo a charge transfer reaction. So
on
oxidation,
one side, copper is going to be plating or dissolving, and that's probably less than ideal.
Yeah, you might not want that to happen. That's what has to happen for electrons have to move through some kind of chemical reaction to get reduced, and then they have to get oxidized down the other side. You might not want that, but you can get charge to move, and that's the same thing that's happening.
It also
here.
Might not be maybe as fast necessarily. Like, for example, if the driving force that naturally occurs in this process is not like high enough that the electron transfer isn't great. Now, copper's usually pretty good. I'm just saying, like, maybe it doesn't transfer that quickly, and it's actually making the whole thing slow down.
Yeah, I think it's because the thing that'll govern the rate is going to be the rate of electron transfer here.
Yeah.
Right. That's going to govern, because electrons move super, as you said, super fast.
Yeah, they move
copper.
fast, but how? But the
rate limiting
kinetics.
step. Yeah, the kinetics are here all at the surface.
Exactly. You got more things to contend
I have
with.
all these other things to contend with. So,
that's a cool idea. I've never thought of that, to be honest.
Yeah. And if you're if you're trying to study a reaction here, this is going to be, or here, zinc instead, your copper is gonna limit the current. Remember, you only measure one current in this whole thing, right? So it's gonna get limited by the slowest process.
So you're gonna be measuring current somewhere you don't really want to be measuring it.
Yeah,
sort of. It's a rate limiting thing.
It's a rate limiting
or
thing.
Could, at least it likely will be. So
yeah, it will likely be a rate limiting thing.
That's a cool thought. I've never really thought about that before. You learn something new. That's
Yeah.
why 100 episodes and you learn something new. Look at that.
Yeah, that's right. It's a great question.
I like that question.
That was a very good question.
Yeah, I do like that question. All right, Anonymous, I promise we didn't skip
you. Yeah.
It was a salt bridge related question just after yours.
Sense.
So it made sense to kind of do a continuation. But let me get to your question. And actually, this is an excuse for me to even answer it in a full way that I've had ready for 2 weeks.
Yeah.
And because there's always so many questions I didn't get to. So I'm going to try to go through this pretty quickly. I do see there's other questions.
Yep, we will.
But I'm not just going to answer about a fuel cell. I'm going to answer about electrolyzers and why they're different. Okay. I've been dying to answer this because a couple of weeks ago, someone asked about the polarization curve for an electrolyzer. And I thought I had the answer and I was almost right, but I was not. And I want to sort of talk through those differences. So what I'll do is I'll show you about a fuel cell and an electrolyzer and how they work basically. So let me start animating and then get to this. All right. Share this presentation. Okay. So let me know if it's not showing.
Yep,
so a fuel cell is a device that includes an anode, a cathode. There's a electrochemical process that occurs at each side. Electrons are transferred through an external circuit. And just like the salt bridge thing we just talked about, actually, there's a membrane through which ionic transfer occurs. I'll talk about a proton exchange membrane fuel cell as a specific example because it's the most common one, but that'll be an illustration of how fuel cells work for you. So in a proton exchange membrane fuel cell or a PEM fuel cell, it's a device that generates energy through the electrochemical reaction of hydrogen and oxygen. On the anode side, we flow hydrogen gas and we perform the backwards of the hydrogen evolution reaction. So it's like the hydrogen, we're oxidizing hydrogen. So hydrogen at the anode is oxidized to form 2 protons and 2 electrons. It's a very quick reaction. The electrons go through the external circuit. That's where your electricity comes from. And the protons go through the membrane, usually naphthalene. On the cathode side, we flow oxygen or air. Okay. And at the cathode side, we have the rate limiting step, which is the oxygen reduction reaction. That's why so many people study it, because it's the rate limiting reaction in a PEM fuel cell. And at the cathode side, the electrons that were generated at the anode and went through the external circuit to power your car or your house or your flying blimp, whatever you're using, join up with the protons that also went through the membrane from your anode side with the oxygen. And then you have oxygen with 4 protons, 4 electrons makes water. So the aggregate result of a PEM fuel cell is that hydrogen and oxygen are split separately to produce water as a byproduct, and you get electricity out of it. Okay. An electrolyzer is a backwards fuel cell is one way to think about it. Okay. So what we're doing is instead of getting water as a product, water is the reactant. We flow water at the anode side. We do the opposite of the oxygen reduction reaction, which is the oxygen evolution reaction. And that is the rate limiting step. And this time it's at the anode. So the anode is where the oxidation reaction occurs. That's why we call it the anode. That's the terminology. That's what it means. We have to add energy to make this happen. We split water up into oxygen gas. So that's our product. And then we get electrons and protons. Electrons travel through the external circuit. Protons go through the membrane, meet up at the other side. There's actually no fuel at the cathode. Usually we just have a carrier gas like argon or nitrogen or something of that nature. And essentially the reduction that occurs at the cathode is those protons and electrons recombine to form hydrogen gas, which is our product. And so in this case, our reactant is water. We get oxygen and hydrogen. And so we're getting fuel, basically hydrogen and oxygen gas as our products, and we have to provide energy to make that happen. All right. So the fundamental things about this are related to the potentials of each cell as well as the polarization curves. And so what I'll step through a little bit here are those different potentials, which I want to do to differentiate between fuel cells and electrolyzers. So the potential of the oxygen reduction reaction, the standard E0. So for a fuel cell, I'm trying to relate both of these together, right? For a fuel cell, it's on the cathode and the E0 is 1.23 volts, okay? So that E0 on an electrolyzer is over here at the anode. So 1.23 volts. I want to use a different color actually. I'm trying to do this. I have like my own little color scheme here. Anode is blue and cathode is red. Okay. Now, for a fuel cell, the hydrogen evolution or hydrogen reduction, hydrogen oxidation reaction, that is like the standard reaction. And so its E0 is 0. This is the standard reaction with which we basically judge everything.
Is there a hold on? I'm not seeing your
I'm not sharing
share
anymore.
Screen.
Yeah, that's fair.
Did that happen from
I stopped the presentation and then I stopped sharing.
Okay.
So yeah, that would be good to know. Here we go.
I was like, oh,
yeah, that would be good to see. Okay. So sorry, here's the animations were working and then I stopped sharing. But my point is, here's the fuel cell at the top, is the cathode and anode reaction, electrolyzer at the bottom, and the cathode and anode reaction, right? As I just showed. And so the cathode reaction down here is the hydrogen evolution reaction, and this one is 0. So E0 is 0. All right. Now, the E cell, the potential of the device itself, okay, is equal to the difference between these two. Now, I have to step through this. I know this is a little complicated. In a fuel cell, we put the working electrode on the cathode. Okay, so this is where we put the working electrode, and we put the counter and the reference electrode on the anode. All right. With an electrolyzer, it's the exact opposite. On the cathode, we put the counter and the reference. Okay. And on the anode, we put the working. So when we talk about what the voltage of the cell is, it's always the potential of the working minus the potential of the counter. So the E cell of my fuel cell, like the voltage, the potential of this cell, it's E working minus E counter in reference, right? Which is 1.23 minus 0. So E cell is 1.23 for a fuel cell. So that's the voltage of a fuel cell. On an electrolyzer, it's the same math, right? Because it's E cell, it's just not cathode minus anode. It's working minus counter. In this case, it's the same. So it's 1.23 minus 0. So the point is here, we have the same voltage in an electrolyzer and a fuel cell, okay? The tricky part, so the E cell for a fuel cell, they're both the same. The tricky part is what do the polarization curves look like and what do the voltages of each look like? So what's critical is that for a cathode reaction, where there's a reduction reaction occurring, recognize that the potential must be less than E0 for a reduction to occur. This is just like standard electrochemistry. When the voltage or the potential of a reaction is less than E0, that reduction will occur. When it is greater than E0, let's say on this side, the oxidation will occur. So what we have is a situation where we want to push the potential. I'm going to delete this because it's taking up space. We want to push the potential on one side greater than the E0 and on one side less than. So let's just put an example for that, right? So if on this side right here for the cathode, let's just look up above this line here. E has to be less than E0. So let's say the E of my cathode is 1 volt, 1.0 volts. That means that I'm going to make this reduction happen. That's good, right? And over here, E of my anode has to be greater. So let's say that's 0.2 volts. Okay, so that's greater than 0. So the oxidation is going to happen. That means that this reaction starts to occur. Well, what's my E cell? Right? It's working minus counter. So it's 1 minus 0.2. It's 0.8. All right. So what this means is that a fuel cell, in order to get it to work, to do these reactions of interest, I have to drop the voltage below the E cell of 1.23. I have to go down, drop the voltage down, and then I drive those reactions of interest. Well, that's good because that's the voltage. That's the energy I have. I can lower that voltage and then I get energy out of it. But that's how much voltage it's giving me. I can drop the voltage and I get energy out of it. Okay. Now the opposite is going to happen with an electrolyzer. Okay. So again, I need E to be less than E0. So let's say for this cathode, I need this to be less than that, right? So this, let's say, is minus 0.2 volts. Now on the anode, this has to be greater than to make the anode reaction happen. So let's say my anode has to be greater than 1.23. So let's say it's 1.4. What is the E cell of my electrolyzer? Well, it's working minus counter, which is 1.4 minus 0.2. So that's 1.6. So what does that mean? Well, I have to go higher than 1.23 volts to make the electrolyzer do the reactions that I care about. That means I have to put energy in. I need more voltage. I have to put energy in, hence why it is a device that requires power to produce a product. And so all it means, and this is the last thing I'll say here, and then we'll move on, because I know I've talked more about this than was asked, but I had to kind of clarify this, is that the polarization curve of a fuel cell, which is where we plot current on the x-axis and potential or voltage on the y-axis, we start at 1.23, maybe not exactly that high, but typically, if we have a perfect fuel cell, 1.23. And what we do is we drop the voltage and we get some current, and then eventually it kind of tapers off. But this is how a fuel cell works. And so what we're doing is all in the voltages in this region, we have a situation where our E is less than E0 at the cathode, and our E at the anode is greater than E0. So we're driving those reactions of interest, and that occurs by simply lowering the voltage and using it to our advantage. Electrolyzer, it's the exact opposite. Okay. So if the polarization curve for an electrolyzer, this is where I screwed up last time. I was thinking it was a negative voltage, and that's not correct. It's positive. So we still have 1.23 because of where the working electrode is. Now this is the working electrode, and this is the counter and the reference. So what we're doing here is now we have to raise the voltage. And so we get something that looks kind of like that. And so at these voltages up here, we end up with E at the cathode being less than E0. So it goes to negative values, basically. It's less than 0, right? And the E at the anode is still greater than E0, but now that's greater than 1.23. So I'm getting 1.4, 1.5, 1.6, and I'm getting minus 0.2, minus 0.3, minus 0.4. So the voltage just goes ever and ever larger. I have to add more energy into it. I have to raise the voltage. That takes energy. It takes energy to raise the voltage of something. But in doing so, I get oxygen and hydrogen gas. That's the point. So I hope that clarifies those two different things. That's how the polarization curves and the operation of fuel cells and electrolyzers are different. And I'm very happy to do that now to clarify that for myself, because I mistakenly wrote or talked about how the electrolyzer works, and I was off. So there you go. Hopefully that answers your fuel cell question, and then also just kind of talks through those two different ones. And the next question is very much along Alex's line. Here.
Yeah.
What is the Nernst equation?
Also Nernst equation. So the Nernst equation, Favorite equation of all.
That's right.
It feels like the favorite equation of all time.
It wouldn't be the 100th episode if you weren't talking about the Nernst equation.
I know. Well, that's because the Nernst equation is so useful in so many different applications.
Mhm.
But this is the Nernst equation. It's this guy right here. And the Nernst equation is very simple. For a redox reaction where you have, say, an oxidized species plus an electron, it's in equilibrium to form a reduced species. The potential of this reaction, or the potential of, say, an electrode where this reaction is occurring, is equal to the standard the standard, E naught, the standard potential, which is just a potential at 1 molar, 1 atmosphere, 25 degrees C, or 289 Kelvin. Standard potential minus RT over NF, the gas constant, temperature divided by number of electrons transferred, various constant, times the natural log of the activities, or most of the time we use concentration of the oxidized and the reduced species. So the way I like to think about this equation is, if I have some kind of electrode in solution, it has some kind of potential, some kind of what we may call like inner potential, sometimes represented by like as a phi or something like that. And this value will go up or down depending on what these guys are. And so the thing I like about this equation so much, it's the reason why it's my favorite equation, is that in electrochemistry, when you're doing experiments like cyclic voltammetry or something like that, what we do is we change E, and when we change E, we change the ratio of these two concentrations. But then at the same time, if we didn't have a potentiostat and we wanted to change the potential, we could just add some more of the reduced species, or some more of the oxidized species, and then we can get the E to change. And so this happens on working electrodes, but this is also the same equation that governs how a reference electrode changes. And that's basically it. This is also at equilibrium. So this is an equilibrium expression. Equilibrium. And when you're doing like cyclic voltammetry, this also assumes that there's like very fast electron transfer kinetics. And when you're doing CV and you're getting these voltammograms and stuff like that, the system, you get this nice duck shape oftentimes because as you change the potential, this ratio is changing, or it's adjusting to match the potential of the electrode. So as your E or your potential is changing, current has to flow to maintain the Nernst equation. So that's what the Nernst equation is in kind of very brief, simple terms, sort of say. And then he has one last question, which is something that I don't actually know very much about. Anonymous asks, what is Kohlrausch's law and what are its applications?
Yeah, it's a molar conductivity law.
Mhm.
My understanding, I've learned about Ostwald's law when I was in undergraduate, I believe, and it's like I think Ostwald's law, or law of diffusion, or law of dissolution, or something like that. It's been a while, but it's something like for a weak acid, if you have if you have like HA as a weak acid goes to H plus A minus, and this is like acetic acid, or which is some weak acid or whatever. You have basically, right? Is it Q, or I know it's kind of like Nernst equation actually, right?
Yeah.
Similar phenomenon, but over HA. This is, so the concentrations, it's technically activities, but it's really concentrations.
Yeah.
And this is the K, like the right. And so you have a KSP is a solubility for something. It's a similar phenomenon, but this what differentiates weak and strong and weak acids, right? So a strong acid, we say fully dissociates, like 100% of. So 1 molar of, like 1 molar HCl gives you 1 molar H plus. Like that's
Mhm.
you know, right, it's a strong acid. But you know, 1 molar whatever, like acetic acid
Mhm.
does not necessarily give you 1 molar H plus. You know, there's a KS, there's a KA is KA, right?
Well, yeah.
KH,
No, Ka
it's been
is
so
the
long.
equilibrium constant
Yeah.
for an acid, and that's where you get like
That's where you get
pKa's
pKa and
because
pH
you
and
take the
stuff.
negative
Yeah.
log of that. Yeah.
So anyway, I don't want to waylay on the acid dissolution thing. My point is that this, I believe, is an outcropping from Kohlrausch's law, which is effectively to say that the summary of the conductivity is equal to its component parts, something of that nature.
Mm.
I don't know that I can explain it too much better than that, but it's something along those lines. And so part of your question was specifically what are its applications, and I believe that's sort of where it goes to. It's like an infinite dilution theory, which is you extrapolate to infinite dilution to get some part of it involves that, and it's like the conductivity of species A plus times its concentration plus the conductivity of species B gives you the total conductivity. It's like a summary. That's again my sort of limited understanding of Kohlrausch's law, and then through that you get things like what I just described, which is what leads to the conductivities are the way they add up, and then you can draw conclusions about the dissolution, and then it leads to that kind of stuff. So I think that's roughly accurate. I might be missing some details, and you know, it's more of a chemistry concept than electrochemistry per se, although obviously it has applications to electrochemistry with electrolyte and things like that. But I hope that kind of covers it to a limited degree from what I understand. Hopefully that's somewhat satisfactory.
So we have a question. First, actually, before we begin with any more questions, just want to say thank you to Jess for becoming a tier 2 member. Thank you
very much, Jess.
On our 100 episode. It's always nice to have people join and support our YouTube channel through membership. So we really appreciate it. We will get to your question as soon as we can. We do try to get the questions in order as time permits. But Weissam has a question. Please, can we calculate turnover frequency for hydrogen evolution using ECSA or double layer capacitance instead of the number of active sites? If yes, how exactly is it done? Thanks a lot. We had a question like this similar last
is becoming
time.
to ask us anything about turnover frequency.
Yeah. Yeah, we talked about this on the last one, but we came to the conclusion that I don't think electrochemically active. Well, I don't think double layer capacitance for one.
That's not going to do it.
Is going to help you determine the turnover frequency. I don't think that's
I don't think ECSA is either. That's an area. That's not. Turnover frequency is the amount of stuff you get per catalyst reacting.
Yeah.
Right. So it's like, I always forget the unit. We talked about last week again.
Yeah.
But
and what I used last time to kind of talk about or describe it, and what he's doing. He's doing hydrogen evolution.
Yeah.
Oh wait, no, but here's the thing. Is it the turnover frequency for like the hydrogen evolution reaction, or are you using hydrogen evolution to determine ECSA?
Yeah, if it's the
last, like I need a comma to really know, clarifying, like, because if it's hydrogen evolution, it's because hydrogen evolution in a way, like hydrogen absorption, maybe he meant, if he wanted to do hydrogen absorption, but generally speaking, I don't know enough. I really don't know enough about ECSA or about turnover frequency. But in general, I should probably have asked one of my colleagues. Someone who does. I know Kate Wally from Rutgers does electrocatalysis. So she deals with this, but this is for like the homogeneous reaction. So in techniques like cyclic voltammetry, people usually will do this. They'll get like a CV associated with like, this is catalyst without catalyst, and that's without substrate. So the thing it's doing catalysis on, substrate. And then
they'll do catalysis, and I'll do this in red. Oops. Oh, sorry. I keep hitting the wrong button. Nope, too thick. Not thick enough. Then they'll do the same thing, catalysis in red, and then they're like, oh, I got this massive current, and it tends to be irreversible in a way. And this is catalyst. This is the catalyst with the substrate. And I keep I'm not spelling this right. Substrate. This is S. And basically, the idea is you compare, like, what's the current here at the peak and what's the current here at the peak. And that gives you like a rough estimation of things like turnover frequency, like how many cycles per se is your catalyst turning over to form hydrogen. Of course, there's a number of electrons that are involved in the catalytic process, but I don't know. But you may be talking about heterogeneous catalysis, and that's a whole like different story altogether. So I'm not sure we can help too much more with that. But this is another thing.
Turnover frequency is one that I never done myself, and it seems like it's a ubiquitous kind of phenomenon or quantity, I guess, where there's no right or wrong way. So you're trying to figure out how much of a thing happens per catalyst.
Yeah.
You're right. It's like, well, how much of a thing happens could be a current. It could be, like you said, like per active site, per concentration.
Yeah.
There's a lot of ways to interpret this. It's, I don't know why, if it's just a coincidence we've had a lot of these questions the last couple of weeks, or it's like a quantity that more and more people are interested in for one reason or another.
Yeah.
I have to kind of dig into this.
I made a note to myself about it. Like, yeah, I need to figure out turnover frequency for homogeneous and heterogeneous catalysis, but I never did it because I was well, I only didn't do it because I was reading about transference, because we also got questions about
the transference number.
Someone asked about migration current, and I'm like, what is this migration current? And it turns out they use migration current in like calculating the transference number, or and I'm like, oh,
there's
gosh,
always too many things that we just don't know anything about.
That's okay.
We try. We will eventually know all the things.
Yeah.
Through the forced learning of all of you fine people asking these questions.
At 200 episodes, I'm pretty sure we'll know everything by then.
So only 100 more to go.
100 more to go.
Until then, we'll have to hopefully that's some answer for you. And we'll move on here to a name that certainly we can't pronounce, but they've asked, what are the limitations of a two-electrode cell in amperometry? Limitations of a two-electrode cell in amperometry. Well, obviously, without having a reference electrode present, the one limitation is knowledge of the potential, whether it's drifting or things of that nature. So two-electrode cell gives you a voltage between the two electrodes that you're testing, and you only know what their voltage is with respect to each other. If either of them moves or drifts in their potential, you have no reference point. So the tricky part, I suppose you could say, with two-electrode amperometry would be that if how do I say this? If the reaction you're trying to drive requires a certain potential at the working electrode, you don't have a good way to guarantee over the duration of your amperometric experiment that potential is maintained. If something is drifting, it will go, you know what I mean? You have no control over that. If you have a reference electrode, you do, right? You have a non-polarizable standard against which you can set your working electrode potential to drive the reaction of interest, for instance. And then the counter electrode is the one that's going to drift around to give you what you need, but you'll be able to adequately drive the reaction of interest. So in other words, like if you need 400 millivolts versus NHE, I'm just making up a number, at your working electrode to drive the reaction of interest to produce whatever product, and you say, okay, well, I'm going to make this 600 millivolts, applied potential between working and counter. Okay, and your counter electrode is at 0, Well, then your working's at 600 and it's over 400. You're good. You're driving the reaction of interest. But let's say after 80 microseconds, the counter electrode wildly increases its voltage up to 400 millivolts. Now, your working electrode is only at 200. It's like gone down too far. Like you have no control over that. Whenever the counter electrode moves, your difference is always going to be 600 because that's what the potentiostat's told to do. So that kind of lack of control in a two-electrode system can be problematic if you need a certain potential at the working electrode to drive a reaction of interest, because you can't guarantee the voltage will remain where you want it to be without a reference. So I think that's how.
That's good. That's a very good answer.
How I would say that. So.
All right, moving on. This is another.
Sorry, I was trying to end it and it was already ended.
Oh, yeah.
Go ahead.
This looks like another question kind of up your alley. Hello, this is from Saulo. Hello, how to select a suitable electrochemical circuit for modeling, I guess specifically for HER. And I believe you're referring to an equivalent circuit for like EIS or impedance modeling.
Yeah. So if you're looking for a suitable model for HER,
well, you usually determine the circuit based on like the electrode, right? Like the electrode configuration. And if you have just a bare electrode surface, sometimes you model these kinds of reactions as just Randall circuits with like a diffusion element.
Yeah, that's one possible. I'm just trying to think.
If you have a heterogeneous catalyst with a thin film, it's another way. Or are you going into the more detailed?
Tend to see. I think Randall's element's pretty common. I know one of the things you get with hydrogen evolution reaction EIS data is a whole lot of crazy noise.
Yeah, you'll have a lot of that
because you're applying a negative potential of some sort to generate hydrogen. You're generating gas, which is messing with your electrode, and it just makes it really tricky and it gets noisy, especially at low frequencies. So I'll just propose a couple of things. I mean, so the short answer is that it depends on what your specific system shows, and that sometimes guides which model you pick. But if your Nyquist plot, for instance, might look like for HE, let me just put HER. This is hydrogen evolution reaction. It'll probably look something like that, or it'll just be. I'm drawing really poorly. That's kind of like flattening it out weirdly. And don't worry about the size. I'm just drawing them so you can kind of see. You might get something like this. Shape. Yeah. Probably one of those two is what you are likely to see. Depends on what potential you're applying and all those kinds of things. But I should do the same color scheme so it makes sense. The red one would be like a Randall's circuit. So you'll have a leading resistor, and then I can't draw it all. I'm all out of whack. It's 100 episodes.
It's 100 episodes.
100 episodes. That's what I'm going to keep doing. That's my excuse. It's 100 episodes.
It's 100 episodes.
Yeah.
So gotta do this thing. 100 episodes.
100 episodes. 100 episodes. 100 episodes. We're at the set. I'm 100 years old. That's what it feels like.
Yeah. That's
so this is a Randall's circuit. It's the most standard sort of circuit where you have this charge transfer resistance right here, and you have your roughly 45-degree line where your Warburg, and that's diffusion. The other possibility is you might just have a leading resistor and then a single, we call this a Voigt element sometimes, or just an RC. This could be a constant phase element or a capacitor, but that's just like one semicircle. So that's another possibility. Sometimes you can have what's known as an embedded model, which can present itself the same as one of these, but it might be something like this, which is a bit of a weird looking thing. Let me see if I can draw it without screwing it up. So you have a resistor here, and then you have a resistor and a capacitor here, and you have a capacitor up here. So you might have like multiple. It's almost like this one here is, we sometimes call this the embedded model. So this is like embedded within this one. You see what I mean? Hopefully that makes sense. We call this embedded. That's one possibility. as well. So sometimes you might get 2 Randall's elements. It really, again, some of it depends on what your data presents itself as. So those are just 2 examples. And sometimes the way it looks educates you as to which model you can pick. But those are just some possibilities. And there's no one answer, actually, right? Unfortunately, it's not that simple. It depends on what your data looks like. It can inform the kinds of reactions that are occurring on your surface. And so those are just a couple of possibilities. But go ahead and take a look in the literature as well and see what people are using to apply. And again, like I said, it's going to depend on what potential you do your EIS at. If you have very strong overpotential, you might get more reactions occurring or whatever. If you have a very small overpotential or you don't apply enough, of a driving force, you might have a very big semicircle because the charge transfer resistance is really high.
And it seems like we've entered the phase of EIS questions because we got like a few in a
well, great.
like 4 in a row actually.
All right, good.
Which is great.
Excellent.
Aniruda, I think I pronounced that correctly, asks, suppose in the EIS we say we saw 3 semicircles. I use 3 RC circuits for the fitting. How can I know which RC circuit belongs to which semicircle?
They go in order of time constant.
Yes.
Typically in order of the capacitors or Qs is the quickest way to do it because usually the Rs aren't so different that they affect it.
Yeah, so, it's like
actually, why am I sharing this?
Software. So with every semicircle, are you gonna?
I'm gonna share our software. It's
okay, it's probably a lot easier.
Yeah, it's almost like we developed this software as a company called Aftermath Blue. It's almost like it would be really useful to answer this kind of question.
Yeah.
Can you believe it? Okay, let me illustrate for you. They go in order on the Nyquist plot from left to right. Let me delete this shrapnel. I meant to do that later. All right, 3 RCs. I have it already built. I don't even have to draw it. It's already ready. Look at that.
Yeah. Okay. All right.
So here's 3 RCs. Don't worry about it. I'll make the Nyquist plot look pretty in a second. Give me a sec. Let me zoom out a little so I have some space. All right, so I've got a leading resistor. Let's just make this small because I don't really want to deal with it. All right, let's just set every resistor to 100. Okay, let's just make them all 100. So all the charge transfer resistances are the same. Now that's obviously almost never going to be exactly the case. Okay, but the point is that resistances will vary to some degree, but not a huge degree to which the extent to which the capacitors or the CPEs will vary. Okay. Capacitors or CPEs will vary by orders of magnitude. It's probably not quite enough. Let me make the separation a little more. If I go too much, I won't see it. I can't do much about the high frequency. I'm just tinkering with the parameters so you can see stuff. Just give me a moment. I promise it'll be worth it.
And if you want to, you can also
let's go lower. So
play with this software as well. Yes. We offer this as a EIS circuit fitting and simulation software.
You can purchase this
that can be purchased, so you can actually play with all these different RCs and circuit models and stuff like that.
Yeah.
You did a great job.
All right, so now what I'm actually going to do. So here's 3 semicircles. You got three little Mickey Mouse ears here, right? Okay. And they're very distinct. So which one is which, right? Okay. Well, they're all at 100. So I have like they're by number here. So R2 Q2, R3 Q3, and R4 Q4. Okay. The widths of each of these semicircle correspond to the resistor values. So right now they're all the same. So what I'm going to show you is that R2 is the first one. I'm going to make that the smallest semicircle. That gets bigger or smaller. Whoop, 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 whoop. There we go, right? So I've got that at about 40. R4 is the biggest one. That's the last one. And that one's right there, right? So which one is which, right? It goes in order on the Nyquist plot from left to right. On the Bode plot, it's right to left. But typically we look at Nyquist plots because we're looking at semicircles, okay? The first semicircle that appears has the smallest capacitor, or Q. So in this case, it's like 32 nanofarads, right? The second one, I just changed the R so you can distinguish between them. That's the next biggest capacitor. right? I'm going to do this for a second too. So here's the plot. Let me make it orthonormal. I'm going to copy it. I'm going to stop sharing. I'm going to copy it into PowerPoint so I can draw on it. So I can do more fun doodles. All right, here's the plot. All right. So here we have, I'll just say C1, C2, and C3. There's resistors here, but these are the capacitors associated with those RCs, right? So this is where we have like R1 or R0, whatever. And then we have 3 of these, right? Terrible drawing.
All good.
It's like I'm running out of space because the Nyquist plot thing is in the
Nyquist.
way. I'm like, I have to
The label Nyquist plots there.
Right.
Yeah.
So this is C1, C2, and C3, right? This is for C1 is less than C2 is less than C3. Okay. The biggest capacitor appears further on the right. The smallest capacitance appears first. Another way to say this is that this is high frequency over here. Yeah, high frequency. My drawing skills are like at a 0 today. Low frequency is on this side. Okay. So what we have is at high frequency, the lowest capacitor value of the 3 appears. And at the lowest frequency at the right, the highest capacitance, appears. That's the way they appear. I want to say one more important thing about this, as I tend to try to share in my webinars when I give webinars about impedance, which you can find on our YouTube channel as well. Do not mistake this phenomenon of where these RCs appear for thinking that they appear in that order. That is not what happens. These are all occurring at the same time, simultaneously on your electrode surface. It is not the case that this first process occurs, like this first semicircle appears, and then like 25 minutes later, this semicircle appears and that charge transfer process happens. And then like next Tuesday, when that one's all done, this next one happens. That is not it. Not it. X.
You can't undo it. No,
I can't undo it. I'm just going to stop sharing. Okay. This is a fundamental thing that's very important. Impedance is a way to probe electrochemical processes that are occurring at the same time, but at different speeds. The reason that C3 occurs at lower frequencies over on the right of your Nyquist plot, and that C1 happens at higher frequencies is because it's faster, not because it's happening before or after. They're happening at the same time. They're just happening at different speeds. A process with a smaller capacitance happens quicker. It's faster kinetics, basically. Yeah, the speed is faster, but it's still happening at the same time. Now, it might finish first, like in a microsecond compared to 100 microseconds. Like it finishes because it's faster than the C3 process, right? But they're not, it doesn't like happen like 1 and then 2, and like this one happens and then this one happens and then this one happens. They're happening at the same time, just at different speeds. And that's why impedance is useful. It allows you to see and quantitatively analyze each one individually, because I can probe them by frequency, which is speed. Frequency is the speed of measurement, right? It's the speed of the sine wave that I'm probing my system. Okay. I hope that answers your question. And I hope that clears up that. I know that's a I know I just went out on a limb, but a lot of people have that misconception. So I hope that kind of clears that up for some people who tend to think that the Nyquist plot semicircles is like the order things happen, and that's not the case.
And similarly, you had like C1, C2, C3, like getting like smaller and bigger in the Nyquist plot, and they had C1, C2, C3 in the circuit diagram. But in the circuit model, the C1s and C2s and C3s can all be in different locations.
Yes.
Because that's based on like what's on the electrode, like what the electrode surface is.
Yeah.
But that order can be whatever.
Yeah, those could be, you can put C2, R2 C2, and then R1 C1, and then R C3. Those can be in different orders.
Yeah, they can be in different orders.
The circuit is equivalently the same.
Yeah,
Mhm.
yeah, that's right.
Yeah.
Yeah. So so that would be important if like you have certain thin films, for example, and you're trying to associate one thin film's charge transfer or you know RC time constant to another thing. Well, the order that they show up in the circuit diagram is not the, you know, it's the order in the Nyquist plot that they show up isn't the same order in your circuit
Yeah,
diagram.
not necessarily. That's
It's not
correct.
necessarily.
Yeah.
So keep that in mind as well. Okay, moving on. 'Cause we have a lot of questions still to get through. Jesse asks, and again, thanks again for joining us as a tier 2 member. In what cases would inductance be used to fit in EIS?
Oh boy, this is your favorite.
Well, yeah, I know. It's if you have an inductive loop.
There's two main reasons. One
Yeah.
is if you have high frequency inductance, and the other is if you have low frequency inductance, which is an inductive loop.
Yeah. Yeah.
The first one isn't really necessary. The second one is very necessary. So type 1 for inductance is probably more common. That's when if your Nyquist plot looks something like this, this data right here is an inductor. That usually comes from cell cable and stuff like that. Basically, that's when you have negative y-axis data, which is like negative minus the imaginary, on your Nyquist plot. That's when you fit an inductor, and then you have the rest of your circuit or whatever it is, something like that, right? That is one way that comes from the cell cables. For the most part, you can often ignore this, but you can fit it if you like to, and that's how you do it. You just add an inductor to the beginning of your circuit or whatever. The second way, which is a very weird and frustrating one, is when you get some kind of a curl at the end like this. That's what we call an inductive loop. And the circuit element that usually fits this is a weird looking one. We'll have a leading resistor, and then we have what looks like RC. I drew that connecting it wrong. And then we have a third tier with a resistor and an inductor. So it's something like this. It's like we call it a corrosion circuit. And it usually looks like this. And basically this kind of a curl occurs at low frequency. The weird part about it is that this value is meaningless. It's my soundbite of the decade. The value of this inductor here, what is it? What does it mean? Well, often it's something like, in the units of inductors, it's something like millihenries or henries. That is enormous. Someday, if you're interested, go to your electronic shop and ask them to show you a 1 Henry inductor. You can find these. It's probably the size of your car. So if you're telling me that there's a massive inductor on a tiny electrode, I don't know how or why. So it's like mathematically, we use an inductor to fit this kind of odd process because there's just no other mathematical and numerical way with which to track and fit this kind of loop phenomenon. There's no other way. We need an inductor. There's some reasons for that. I'm not going to dig into it too much. It's a whole thing. I had talked about it in some of my webinars. I can if you have a follow-up question, but the point is that there's really no way to accomplish this without using an inductor or the concept of inductance. But it flies in the face of circuit fitting, which is that we try to relate the circuit elements and the equivalent circuit to something real. And we are kind of at a loss to do that with this particular model. It comes with the territory, unfortunately. But those are the two most common ways that inductance finds its way into your circuit or into your EIS data.
All right. Moving on, we got a question from David. David says, hi, I'm doing EIS using hydrogels loaded with a conducting polymer as the working electrode, immersed in a PBS solution. As a control, I also test blank hydrogels without the conducting polymer. For the blank hydrogel, the best fit is an RQ equivalent circuit, which results in an almost vertical line in the Nyquist plot. Could you help me explain the physical meaning of this behavior?
First of all, if you have a blank with hydrogel without the conducting polymer, how are you getting any results at all?
Well, it just has a really high impedance.
I mean, for sure it does. I mean, if you're gonna get any electrochemical results in a system with like almost no electrolyte, impedance is the experiment to try.
Yeah.
You know, you're never gonna get DC electrochemistry
Mhm.
with very poor conduct. My point is, having a blank is obviously a good idea in some general sense, but like if you have no electrolyte, I don't know how you're going to get much electrochemistry at all. You have to have electrolyte somehow. So fundamentally there must be some intrinsic conducting, and maybe that's the point of the blank. And if that's the case, that's fine. But the way I am understanding it is that there's no PBS, there's no conducting anything added intentionally to your hydrogel in the blank test. So it's like the electrochemistry is going to be fundamentally difficult. And so what does a vertical line mean? The Nyquist plot, it means just capacitance. Or
Mhm.
or an RQ where R is really, really big. And if R is really big, it might as well not be there. So like having a resistor that's, 10 to the 500 ohms, well, that's such a big resistance that it might as well not be there. It's open. There's no way
Mhm.
current gets through a resistor that large. Like, it's, you know what I mean? There's no difference fundamentally between an infinite resistor and no resistor. And I don't mean a straight wire. I mean having it open, like completely open circuit. So it's just a capacitor, like it's just capacitance. And what that means is the impedance is getting really, really large because your current is really, really small because there's like no conductivity whatsoever. So honestly, it's not an RQ, it's an R in series with a Q or a C, a capacitor, right?
Mhm.
That's what you get for a vertical line, or it might have a slight tilt to it. It's probably, if you were to get an angle, it's like not
Yeah.
90 degrees. It's
Ever
7.
so slightly
Yeah,
different.
exactly. Yeah,
Yeah.
because reality is not um, perfectly capacitive, but that's basically what it
Yeah.
is.
Yeah.
There's no,
Capacity.
you're not going to get any charge transfer processes. There's no conductivity. There's no Faraday processes.
Yeah.
It's just capacitance, and even then, it's like really low conductivity. So your current, your impedance, like I suspect that your y-axis goes to mega ohms at least, maybe giga ohms before long. Like the overall impedance is very, very high because your current is very, very low because your conductivity is very poor.
Yeah.
But that's really it. There's not much going on. It's just
Mhm.
just capacitance, and at that, it's a very low amount of it. It's a very small capacitor, basically. So
Yeah.
yeah. So I think
Okay.
that's
I think that's what it
I
is.
think that's what's going on with with no appreciable amount of electrolyte in your solution. That's probably what it is. So
Okay.
Murat
Alright.
Khan, I think, is next.
Yes.
So it says, what could a shift of peak current density to higher potentials in the oxidation part, but no shift in the reduction part mean while doing CV? Could that be an asymmetry?
I'm not so sure. I need to like
Like you have your peaks and the oxidation's going this way, but the reduction's staying the same.
yeah.
Like
But like what's the change?
yeah,
Like is it
like
the scan rate?
yeah,
Are you
that's
going to like faster scan
or
rates
just over
or
time.
just over time
Yeah.
or like
Yeah,
like
what caused that?
yeah, what there has to be a difference between like what's causing the shift.
Mhm.
Like chemically what you're doing, and then we can try to figure out like, okay, what does it mean that like you're not getting a shift in like the reduction part. So basically at least we can tell like it's probably not an IR issue. um yeah, most likely it's not like you have some solution resistance issue because both of those would change, those they would both shift.
Mhm.
um they also could be, I'd have to see the voltammogram. They could be not very related. Like they could be somewhat related to each other, but not really related. I've done some voltammograms where like I get like an irreversible peak, or if I sweep way too positive, I get some other stuff happening
Mm.
that's changing the system, and I have a peak, a reduction peak associated with that thing, not the main peak. So making sure that these things are kind of coupled. I I think I really would have to see it and know a little bit more
Yeah.
about what exactly. Like, yeah, what's the change? So if you want to comment,
yeah, let us know what is the change leading to that.
Yeah.
And we can try to.
And then we can try to think about what could be happening. It may even be a chemical response too. If you have a coupled chemical reaction, that definitely can happen. Like some reactions are like acid catalyzed. So if you change the pH, you actually start to see a positive shift, but the reduction actually doesn't cause a change. So there are weird things like that that can happen.
Yeah.
Okay, the next question from Zhengyu Chen is I have a question about 3-electrode system. He says, why we can't just control the voltage between working and reference and measure the corresponding on counter electrode? What is the key point of the feedback loop in a potentiostat? So let's see if we can unpack that. I brought up the circuit of a potentiostat. We can unpack this a little bit. I'll talk a little bit about this, but the potential in the potentiostat circuit, you tell the potentiostat from the potentiostat set point what potential you want. So you say that's like maybe like +1 volt, and you want this versus your reference electrode. So you apply 1 volt here into this, what we call the invariant input of this high gain operational amplifier. I also want to make sure I'm understanding the question. Actually, before I continue, I want to make sure I'm understanding the question correctly. It's why can't we just control
the voltage
between the working electrode and measure corresponding on? I don't know what corresponding.
I think part of the question is actually that you can. The second part is good to explain how a feedback loop works, but why can't we control the voltage between the working and reference? Actually, that's exactly what you're doing.
Yeah, so
that is what you're doing. And then measure the corresponding potential on the counter electrode. You can if you have either a bipotentiostat or a countersense.
Yes.
So if the first part of your question, Yucheng, is that why can't we measure the voltage at the counter electrode while we're doing the thing the potentiostat does, which is control the working and reference? You can in two situations. One of them is if you have a bipotentiostat, which has a second working electrode that you can use to measure the counter electrode, or if your potentiostat has a counter electrode sense line. Basically, the potentiostat necessarily controls the potential, the voltage, whatever. We use the word potential in this sort of context, but it's same terminology. But I'm using potential for voltage just to be clear. It controls the potential between working and reference electrode. That is fundamentally what it's doing. The measurement of the counter electrode potential individually can be done. You just need another sense line.
Yeah, or you even use a separate voltmeter.
A separate voltmeter, yeah.
You connect the separate voltmeter to these two guys and watch it change dynamically.
We don't normally do this because we don't normally care. You don't normally need to know what the potential is individually of the counter electrode. It's there to help you accomplish what you need on the working, which is where everything of interest is occurring.
Yeah.
So all of the current and all of the voltage that the counter electrode experiences is done in service of getting the working electrode where you need it to be. But if you care about the counter electrode, you just need another sense.
Yeah.
That's all. And then that's why some potentiostats have a counter sense line, which allows you got to pick the right software program and all that kind of stuff. But basically, it allows you an opportunity to do what Alex has just drawn there, which is have a sensing point additionally between the counter and the reference. So it can be done.
So I got a Yu-Chen. Okay. Yu-Chen, by the way. Okay. And
corresponding current, he says.
Yeah, corresponding
current, not potential of the voltage. So the corresponding current. The current of the counter electrode is the equal and opposite of the working electrode always.
Yes. Yeah.
You are always measuring the current of the counter electrode. You're just not measuring the voltage. So if your question was measure the corresponding current on the counter electrode, you are. The current that you get in your potentiostat is equal and opposite to the counter electrode.
Yeah.
The voltage is not, because of what we just described, the feedback loop, right?
Yeah.
But the current is equal and opposite. So if you have 100 milliamps occurring on your working electrode, your counter electrode does have minus 100 milliamps occurring.
Yeah.
That is equal and opposite.
Yeah, they're the same.
Yes.
Yeah. Hopefully that
hopefully that clears it up for you.
all right. I think I answered the question, so we can move on. We have
Yeah.
like 20 minutes or so.
Yeah, let's try to
Yeah,
so
the comments.
Hasit had asked how to join. I
Oh,
there's a button on the, if you're on YouTube, right? There's a button. Where is it? It's on the.
it's right next to. It says like
Join,
yeah, it's like right next. It's like on the video on the lower left hand corner where it has the channel. To the right of it, there should be a join button.
It's like here.
Approximately, yeah, it's approximately there. A little bit more the other way, towards you, towards you.
My computer screen's in the way.
Yeah, it's there. So yeah, you should see a join button if you.
It's around here.
If you wanted to join our YouTube channel, which we as a member
very much
we appreciate it.
if you
Or just subscribe. Subscribing is also
great. Subscribing, you'll get notifications when we go live, which is this time every week.
Yeah.
But your next question we can get to.
Yes.
So this is how. Oh, sorry. I think.
I think
it's like opening the car door the second you're unlocking it.
Yeah. Okay. You.
I got it.
You got it. Okay.
All right. Crisis averted. Okay. How affect the diffusion layer to the peak current? The diffusion layer is what. So in a voltammogram, basically, the diffusion layer growth is what results in a peak. I'm trying to think if there's a way to answer this question in a slightly different context. So
I can also bring up I think I have a slide that might help.
So when your current increases in a voltammogram, it increases because of kinetics, and then it hits, and when the peak occurs and the current starts to decay, that happens because the diffusion layer is growing and becomes thicker, and the mass transport becomes the limiting reaction or the limiting step, so to speak. And that causes the peak to decay. But the just in terms of directly answering the question, like the actual peak current isn't a function of the diffusion layer; it's a function of like the scan rate and right, I'm just thinking like direct, like in other words, the peak current, like the actual current that you get, at the peak, that's a function of like the scan rate.
It is a function, like the like the Randall Sebzich equation.
Right. In other words, I don't know that an answer to this question, literally to the what is being asked, if I'm understanding it correctly, I don't know if there's a correct answer to say that the diffusion layer affects the peak, the current you get. It affects that you get a peak, but does the properties of the diffusion layer affect how high that peak goes? You know what I mean?
Yes.
I don't know that that's the case.
Well, it's like if you think about there's a way of thinking about this, which is that as the diffusion layer thickness, like the diffusion layer thickness governs the current that you get. So that's why rotating disc electrodes kind of work. Like with a rotating disc electrode, you can fix the diffusion layer thickness. You can change it. Normally in a CV experiment for a stationary system, the diffusion layer just happens. Like it goes, it changes, it gets higher, it gets lower. But with a RDE, you can change, you can fix the thickness, and that's why you get a steady state current for those types of things. So, but RDEs don't generate peaks. They generate that limitation. But you could think about the peak current, if you will. I mean, it's like, how does the diffusion layer affect the peak current? I was going to show this
slide, and then
this slide that might help it, which is to think about diffusion. This is just, you have a oxidation reduction reaction, and then you can see this is my voltammogram, or this is my voltammogram. This is the applied potential, and then as I go through, let's say I'm reducing something, so I slowly apply negative current, and then I start to develop this diffusion layer. I generate the reduced species at the surface. So here my diffusion layer is actually super thin, and that's where I kind of like get a peak. But then over time, like I get less, my diffusion layer gets bigger. There's fewer of my oxidized molecules that are around that can actually go to, I'm using my mouse, but I should be using the inking tool. There's fewer of these guys to kind of go, they're diffusing kind of randomly, but they need to get to the electrode surface to undergo that transfer, which is why you get less current. But before you had a lot, you had like so many of these guys around, very easy for them to randomly bump in And oh, I don't know how that happened.
That's fun.
That's fun. But you have ink to shape. Okay.
Oh, you did ink to shape.
Yeah, I accidentally clicked ink to shape instead of
fun.
thickness.
You made it oval. Yeah.
So it's much easier because I have so many of these guys, and so I get more current. And all the guys here, well, they like instantaneously, underwent the electron transfer from here to here. So this happened very quickly, huge current. So yeah, as the diffusion layer thickness gets bigger, your current gets smaller, but the peak is is as you have shown with some of your slides. The peak is the result of the difference between the mass transport limitation and the kinetic limitation.
Yeah.
Where those two meet is where you get a peak in a way. Okay.
Okay, let's see. Try to get through these here.
I think Sidhu is next.
Yeah. Is it necessary to connect the counter electrode for corona amperometry at 0 amps? No. Well, if you're doing OCP, no.
Yeah, I think that
potentiometry.
I'd recommend it generally because it's a controlled. Because
wow. Okay. Oh yeah. So okay.
It's under potentiostat control. Yeah.
No, it's under galvanostatic control. Chronopotentiometry.
It's under galvanostatic control.
So in some sense, there's no difference between OCP and chronopotentiometry at 0 amps. They are like fundamentally or materially the same. From a potentiostat operation perspective, they are not.
Yeah.
From a potentiostat operation perspective, you can imagine OCP, an open circuit potential measurement, is what you're describing, is that internally it is effectively disconnecting the counter electrode and measuring the voltage between the sense lines. A chronopotentiometry measurement is at 0 amps is still a controlled current galvanostatic process, which requires the counter and working electrodes to be connected to drive lines. I would guess it might still work, but I think I wouldn't recommend it. I think if you're doing a galvanostatically controlled process, even if it's 0 amps, you probably should still connect the counter electrode. That is my suggestion, because I know how the potentiostat works, and it is not exactly the same, even if they're effectively and often resulting in the same thing.
Yeah,
if that makes sense.
Because like I think the potentiostat is going to like there's a DAC associated it might have a
with runaway
zero
feedback. Right?
It may run away feedback, even though it's like
anything.
nano something. It's not measuring that. It's going to do something.
It could cause some problems.
It could cause problems
if you're in a galvanostatically controlled experiment and there's no connection to the counter.
Yeah. That might.
But if you're running OCP, I think you can just disconnect the counter, and the potentiostat still works fine.
Yes. Yeah.
Good question though.
That is a good question.
That's another from Hasith, but it's a similar thing. I think. How does the working electrode affect the peak current? I think we kind of just talked about the peak current. I think we'll kind of leave it there.
Working electrode material. More working electrode material.
Material. I missed the material word.
It depends what the reaction is a little bit. If you're talking so the material, okay. If I had gold and platinum, and I was doing a ruthenium hexamine reduction reaction, and I had the same area, I have two different materials, and it's a homogeneous process, the peak current is going to be exactly the same. There's no difference in the peak current, because if the area of the electrode is the same, the concentration of the solution of the thing is the same, and it's a homogeneous process, then peak current's the same. But if it's heterogeneous and it matters what that electrode material is, then you will see some difference. You may not even get a peak, or the peak gets shifted, because there's a potential difference, sort of say. So the peak potential may change if it's like a more heterogeneous surface bound, or it matters what the electrode material is. It may shift the potential a little bit more. But the peak current is dependent on things like the area, concentration, diffusion coefficient, scan rate. But the electrode material itself for a homogeneous reaction shouldn't matter. All right.
Okay.
Okay. Next one. Shruti is asking, how do you calculate ECSA from double layer capacitance?
You'd have to know the specific capacitance of the process that you're looking at. Right. Some processes have like a tabulated, or you can find it in the literature or something, like specific capacitance associated with them, which means like the capacitance of, I'll just make up a thing, and I know it does not, this isn't real, but like the capacitance of a double layer on gold in 1 molar sulfuric acid is 0.7 farads per square meter. Like that might be that's my point. Like you might be able to find something like that. There might be in the same way, the most famous example is the hydrogen adsorption on platinum is associated with a specific charge of 210 microcoulombs per centimeter squared. In a similar way, you might be able to find a specific capacitance of however many farads per meter or square meter for a process. And then when you measure your farads, you just divide. But if you don't have that information, you can't get the ECSA. You need a specific capacitance associated with that electrode or electrolyte. So without that,
Yeah.
I don't know that it's possible.
Yeah, no, I think it's I think you're right. The only other thing is if you if you use the capacitance, and then if you figured out you could use the other equation for capacitance, which is like related to the distance, the area, and the dielectric, then you could figure out you could solve for A if you knew the thickness and stuff.
You have to know the dielectric constant,
Yes,
and what's the distance? What's the
distance
of the Helmholtz layer? There's a lot of assumptions that are being
Yes,
made. I think you could do that, but that would be that would be hard to get an accuracy at best. But
correct.
In theory, that would work.
Yes.
In theory, that is an alternative possibility.
Yeah.
The equation for a capacitor, right? The capacitance is equal to, I'm trying to pull it on my memory. It's like a dielectric times the permittivity in the vacuum, divided by the distance squared or something times the area. It's not something of that nature, right? You find the anyway. You can extract area from that, but you need to have a lot of constants. You have to make a lot of assumptions. I think they'd be tricky.
Yeah. All right. We have about 9 minutes left. It looks like there are
questions.
A bunch of questions. So I kind of want to maybe just get some comments. Let's just get through a couple like random comments. Dooley says, hey guys, successfully defended his PhD thesis this week. And thanks for all that you do with all, and just becoming more familiar with electrochemistry. Happy 100th. Thank you, Doolies. We're very happy that you successfully defend your PhD. It's kind of a surreal experience, actually. And Anonymous had a comment. I'm just trying to get through the comments, the things that we can answer just like super quickly, not even electrochemistry related.
Yeah.
But Anonymous has an electrochemistry test tomorrow. And so let's see, he's trying to, he provide some theoretical, if you can have theoretical knowledge of these topics. And it's just like the electrochemical cells, galvanic cell, conductance of electrolyte solutions, electrolytic cells, electrolysis batteries, corrosion. That sounds like a massive textbook worth of stuff. And if we can't in a few minutes really,
I'm not sure this is a practicality. In a very short time to go over all of those topics in great detail.
I'm sorry.
We tried to, I tried to answer the fuel cell question earlier. We've done our best to answer your questions. I mean, good luck on your test for sure.
Get some sleep.
Get some sleep. There's only so much we can answer in a short amount of time, right? Corrosion is a whole topic. Batteries are a whole topic. Electrolysis, cells, all of these things are big topics that we could talk for hours about. And it's quite the undertaking to try to go through all of that. Let me touch on this really quickly. Simple Rog has said, for discharging a lithium-ion battery before recycling, shall I use a battery discharger, or dipping the battery in NaCl is sufficient? This is a great question. All I wanted to say was that I'm not 100% sure, but my intuition tells me you should probably try to electrochemically discharge your cell, because any other method that would include something like electrolyte, I'm not really familiar with dipping it in
just
NaCl,
short
like,
circuit it basically.
well, that's the point, right?
Yeah.
Is that it's recycling. So you are trying to kill it, the battery, whatever's
Okay.
remaining, so you can extract the materials for use of recycling in some way. So that makes
Mhm.
sense. I just it's like, if you were to have the procedure of and maybe this is fine, and maybe I'm not approaching this the right way, which is possible, but like any method that like instantly short circuits to try to end the battery's life or whatever could be catastrophic. You could destroy it. You could cause a lot of problems. Lithium-ion batteries can get into thermal runaway really quickly. And then if it goes into thermal runaway, there's no recycling. It's gone.
Mhm.
It's going to burn up. So I think it's possible, if you expose it to NaCl, to water, if you just short the anode and the cathode and just let it just self-discharge rapidly, immediately, it could blow up or catch on fire. Like,
Oh yeah.
and again, I may be not aware, which is certainly the case, of a lot of the the science of the battery recycling, which is like a desperately needed thing. Please, more researchers, please work on battery recycling.
Oh yeah.
We're
Yeah.
barreling down this world of like electric cars and all of this, and it's wonderful. This kind of technology is great. I'm obviously an electrochemist and I'm for it, but we need to do something about used batteries, because we can't just keep throwing them into a closet somewhere.
Yeah.
You have graveyards of quote unquote green energy in batteries and cars, and it's like, it's not a sustainable solution. So we need to work on recycling. So I applaud you in that case, but I don't know if a very possibly dangerous and rapid discharge or short circuit kind of a approach to getting to the recycling of a battery is wise, because it's more likely than not to lead to a catastrophic failure in general.
Yeah.
Now, maybe with a battery that's ready for recycling, it's less dangerous because it doesn't have as much energy left, and that might be the case. But my hunch tells me you should probably try to electrochemically discharge it to 0%. Probably have to disassemble it somehow, and then there's chemical steps to extract.
So he should use a potentiostat to discharge it, probably.
In theory, that's
right?
what I would suggest. Yeah. I mean,
Yeah.
because you can literally just take a battery and just short both sides with a piece of metal, a wire.
Yeah.
And it's
but that's dangerous
a lot
because
of heat comes out of that.
yeah.
You get a lot of heat. It can blow up.
Yeah.
It can catch fire.
Yeah. So if you can control the rate with like galvanostatic,
galvanostatically discharge it.
literally.
Like, you can do it quickly. Probably there's probably not a lot of energy left there if you're getting to the recycling stage. But I would caution about the safety of something like that. That's my worry about.
Mhm.
Yeah, let's just open it and dip it in salt and water and let the lithium fizz away. It's like, maybe that's okay in small batteries, but I bet large batteries you could be damaged. It could be dangerous. I'd be worried about the safety. That's my only concern. So,
Okay. And we wanted to get to that question because it's like a safety related.
Yeah, exactly. And
it's like, oh wait, if we don't answer.
And I just wanted to highlight the recycling, as it was such an important process. And it's like, it's not like an attractive one. Like, making batteries and making technology is really fun and exciting. You're like, oh, I'm making the next battery technology. It's going to power a spaceship or some cool thing. And it's like, oh yeah. And then when that's all done, it just sits there and pollutes groundwater. It's like, we need to work on recycling of batteries and these, lithium and cobalt and nickel and manganese and all these materials that are, we're mining
rare
and
earth
everything.
Metals and stuff.
Yeah, there's a lot of effort and energy required to get them out, and they're not necessarily, non-hazardous. We need to do something about these materials. It's a process I don't think we can overlook. I don't want to overlook that process. That's my point.
I would also say I was at a conference not too long ago, but I think it's also a profitable endeavor, because
that would be great. I'm not convinced of that, but that would be great if it is.
So some people were telling me, like, there are these rare earth metals, and if you have, say, I don't know, if you have 10 ppm of a rare earth metal in like an ore and you can extract it, it's profitable. 10 ppm. I'm just like, 10 ppm is a lot. It's like, oh yeah. If you have 100 ppm, you're 10 times more profitable if you can extract all of it. So the fact that you have a thing And I don't know enough about recycling it. I just remember hearing about like the ore, just like if you have such a low concentration of a rare earth metal in the ore, then oh my gosh, it's like, oh, and you can turn it into like research or industrial grade whatever that can be sold. I'm like, oh, super profitable because those things are expensive.
Yeah.
Yeah. So I think it can be
that would be wonderful. I mean,
I think
look, this is a world where
Yeah.
if it can be profitable, someone's going to do it.
Yeah.
And that would be great. I remain skeptical that
Yeah.
the energy input is not exceeding the profitability output.
Yeah,
And
I mean,
that
that may be a
just
thing.
means you need government subsidies or things of that nature to be able to
Yeah.
do something like that, which can be, something that is done for. It's fine. It just in general, as a scientist, I look at this problem as a battery scientist. You're right, and I look at this and I say, I also love battery technology, and it makes me tick, and I like it, right? And I just recognize the fact that we desperately need solutions for the sustainable energy afterthought, right?
Yeah.
Everyone cares about sustainable energy in general, and very few people, I would say, in general, right? Not everybody, but in general, care or think about the after part, because sustainable energy is just like any kind of energy. There's what to do with it afterwards. And, the existing infrastructure, for better or worse, we have procedures for handling, sometimes it's just scrapyard stuff or whatever. We have procedures for like what we do with old cars and old batteries and old stuff. We have a lot of procedures because it's been, 100 years of this, petrol powered cars and whatever. We know a lot about it. We've been living in this world in almost every major country in the world and it's like we're moving into this world, now where with alternative energy sources and batteries and electric cars and all these things. And it's like, it's wonderful. We need to handle the other part of it too. We can't, I feel like we can't barrel down this road so fast without trying to consider how do we deal with the, the waste and recycling is a huge thing. I'm happy to see more and more people like talking about this and studying this. It makes me I'm happy to see that, like, just as a scientist, I want to see efforts being done. It's a smart and like very, good for the environment kind of a thing.
Yeah.
In my opinion. So I'm happy to see that.
Yeah. It's 3:01.
I'm just trying to see if there's anything we can answer quickly. I know, I'm sorry if there's a few questions we kind of can't get to.
We usually encourage you to come early, just like Ahmed did, and just get all his questions like answered super early. We're like full of energy. We can answer them in like great length and detail.
By this point, we're running out of voice.
We're just like, Nernst Equation's this. All right, move on.
Taki asked about our software. I just provided a link to where you can download the software that I show, Aftermath Blue, and then you can purchase circuit fitting licenses. I listed the web page where you can see there's a couple of options. So you can purchase circuit fitting licenses if you want. You can purchase them on our website, or you can contact us and we'll provide you a quotation, however, whatever purchasing it as you prefer. So that's how you can purchase that if you wish. Again, there's a few other questions and everything, but we're going to have to call it here. I think we hopefully tried to get to most of your questions, and I'm very sorry if we didn't get to everybody. We do make our best, but we've reached our time limit here. So we're going to have to call it.
Come early next time. It's really the best way to get your questions answered, because we're only getting more questions, not less questions that can be answered in a 2-hour period of time.
Yeah, we're very, very sorry not to get to everybody, but it's an interesting problem to have. It's like one of those podcasts where they get so many comments, you can't read all the comments.
Yeah, you can't read all the comments.
And when you're I imagine if you're starting a podcast or a live show or something, like we were in the beginning, and you can answer every single question in huge amount of detail and spend as much time on it. And now it's like we're victims of our own success.
Yeah, which happens.
Very much appreciative because of this.
Yeah,
100
episodes right here.
It's crazy. So thank you everybody very much. I'm very sorry for the handful of you. I do see that there's a few questions we just don't have time to get to. So our apologies, but we do our best to answer everybody in the time that we have. And please join us another week. We should be here next week, I think. And
if you're in Montreal,
I'll be in Montreal
next week. You can see Neil.
I was going to mention
the
that. I
ECS
almost
meeting.
forgot. Yes, I'll be at the
Yeah.
Electrochemical Society meeting in Montreal, Quebec, Canada, starting on Monday. So the Pine Research booth will be open in the afternoon to evenings on Monday, Tuesday, and Wednesday. So come say hi if you're there. It'd be good to see people. We like meeting our, YouTube viewers in person. It's always fun to say hello to people and put faces to the YouTube Pokemon names and whatnot. We've had people with Pokemon names.
We have had people with Pokemon
that's a thing,
names.
which we learned afterwards because I don't know much about Pokemon.
Yeah, that's right.
But anyway, it's always a pleasure. So thank you everybody again, and come see me in Montreal. And if not, we'll see you next week. Same 100 episode time, same 100 episode place.
All right. Bye.
Bye everybody.